Yes, sir.
Okay, let's wait for a couple of minutes. We'll start. Okay, let us start. Good morning again. From the start of this course, we have been significantly focusing on analysis and design. Right. So we did a very elaborate discussion on object oriented paradigm along with C++, trying to learn the language support for object orientation and so on. And we did a lot of stuff around those. We looked at the software development life cycle processes as to what all are involved in the entire life cycle of a software development, maintenance, and so on. More from I'd say more from a theoretical perspective, and some of that, a very little tiny part of that is what we are trying to do in our assignments here. And then we looked into more in terms of modeling, unified modeling language, how to model at multiple levels, and that too primarily focused on the behavioral models at the specification level, structural models at the design level, and variety of different behavioral specifications and so on, mostly around the analysis, requirements analysis, design phases primarily. So now for the next couple of lectures, we will spend time on testing. It's something whose importance is the highest in terms of getting the systems right, to build the right system as well. And in terms of attention, not always it gets the due attention. In terms of personal preferences of software engineers as well, the general feeling is testing is a bad job. I'm given to test. We need to change that mindset and actually look at how testing itself could be extremely challenging. And of course, it is a menial, tedious task if you have to sit down and keep on giving input and checking output. It is not a very high-end job. But the real challenge in testing lies in how do you do the test automation. How do you do automation in testing? So if you had given a system, how do you test it? What do you test for? How do you design the tests? How do you drive the test? What can you conclude from the tests? If a test fails, then how can you debug? If you have debugged and fixed a problem, how do you ensure that you have not created more problems in the system, and so on? So testing by itself is not only challenging for the industry, but it's very challenging intellectually and in terms of expertise of an engineer. So I'm going to go through some of those aspects, starting with the basic notion and definitions of testing paradigms, and talk a little bit about some of our industry experience in terms of what it takes to test and to automate tests, more importantly. So this will, this presentation is still on development. I did not have it in this way that I am presenting to you now. So it will keep on. By the time we finish the discussion, the presentation would be fully ready. Okay, so why test? Of course, to make sure things work right. So let us first take a look at some of the dark sides of not having tests properly or not having done enough. So this is a case from 1996 where Ariane 5 flight 501. It's kind of a satellite launching rocket, which you can see that this is on left the Ariane, the beautiful rocket. This is when it is being lighted up, and this is what happened to it 37 seconds after the launch. It just self-destructed itself. Now, finally, when it was all analyzed, it was found that Ariane 5 actually reused code from Ariane 4. Ariane 4 was using Intel processors which were 16-bit signed integer, and Ariane 5 used 64-bit floating point. So what for using the reuse the code of Ariane 4, which was an advisable software engineering step, they converted the 64-bit floating point to 16-bit signed integer value, and in the process, some small positive value became negative. So you can see that feedback was to go up, it kind of became go down, and so on. So floating point number was larger than this, and further disaster has to happen when it has to happen. Further, to improve the efficiency, the exception handling, whatever little was available at that time, not much was there though, those exception handlers were shut off because they slow down the system. So what means that even when all these problems happened, the exception handling could have saved it, but it didn't. And this part was never tested. So because the code was being reused, so everybody believed that it will work, and it led to this disaster. Hundreds of $1 million went down the drain. Couple of others. In 1998, NASA's Mars Climate Orbiter mission to Mars at 125 million was lost in space, simply because in terms of conversion of unit, British system still use that kind of pound, your weight as pound, and foot and all that, liter, I mean gallon and all that. Whereas the rest of the world use the metric system. So there was some simple conversion from English units to metric systems done that were not tested well, and failed, and it was lost in space. On a different system, the EDS child support system, this happened in 2004. There was a bug in terms of incomplete software integration. The modules were tested, but the integration testing, whether they interoperate, was not tested right. The result is about 1.9 million people were overpaid, about 700,000 people were underpaid, about $7 billion were uncollected in child support payments. There was huge backlog, new cases got stuck. US taxpayers paid over $1 billion on this. Right? So you see, it's a very simple software issues that can cause disasters. A smaller one, but an interesting one, Heathrow Terminal. I think this was in early 2000 also. 5 was opening, and it had a very sophisticated new baggage handling system. So before the opening, the staff went overboard, tested it perfectly for 12,000 test pieces of luggage and everything. But the test plan was incomplete. There was no case for removal of a baggage. After a baggage has been put, if it is taken back from the belt and put back again, what will happen? This test case was not there in the plan. But when the system went live, very soon someone had forgotten to put in something. So after putting the baggage, he took it off and then put it back. System got confused, went into self-test, and self-closed itself. And for over 10 days, 40,000 bags failed to travel. About 500 flights were cancelled. Well, so these are classic examples of how test really, I mean, inadequacy of test, what can it cause you? I mean, this was an inadvertent error in 1998, which a student called Robert Tappan Morris, he became famous by the name of Morris worm. He was doing some experiments, and he did not, naturally, as a student, he did not test anything in a closed or limited environment, and it got spread, started crashing. This was actually the first widespread worm attack that happened, which fledged the internet. He was actually convicted for this offense, was fined $10,000. Cleaning up this mess is took as high as $100 million and so on. Incidentally, Morris later on co-founded the famous startup incubator Y Combinator, and is now a professor of MIT. This is the famous disk which contains that Morris worm. Okay, these all were disastrous, but these were all financial. But very often, and this is what really scares me when I fly, is a very large percentage of the mechanism that runs our aircrafts, which come from either Boeing or Airbus, typically, at least the commercial aircrafts. They are software. So Boeing introduced a new 737 MAX jet based on their 737 MAX. And what resulted is nightmare. In October 2018, the Lion Air Flight 610 crashed minutes after taking off. On March 10, 2019, it is as late as that, you can see, just a couple of years back. Ethiopian Airlines Flight 302 crashed minutes after takeoff. All 157 people on board the flight died. And these both flights involved in Boeing's 737 MAX jet. The problem is here at a certain point, to improve the engine efficiency, the software was permitted to overpower all flight functions, trying to mediate the nose lift. Nose lift is required, as you know, as you go up, that you need to put your nose up. The software decided to put it down. The pilot could have overridden that, but the pilot did not know. They were not retrained because 737, they were all 737 pilots. So it was thought that, well, they can fly a 737 MAX, but this small thing. So it is a disastrous effect that happened. 737 MAX, of course, got grounded and so on. Similar things happened with Airbus also. Airbus A400M crashed in Seville after a failed emergency landing during its first flight in 2015 because the electronic control unit, the software in the electronic control unit board malfunctioned. So, I mean, these are just stories I want to share with you because young minds often feel that it is only critical to design. It is only critical to write smart code, but the smartness of the code is not in the form of how cryptic it is or how smartly it is written. Smartness of the code is in terms of how efficient it is, how safe it is. Right. So that's what testing has to really ensure. So with that background, you all know how to test a program: input the data, observe the output, check if the program behaved as expected, and if it does not behave as expected, then note the condition under which it failed, debug and correct. So obviously the question could be that, well, could I check the program for all possible inputs? Now there are two aspects to this. One is it is infeasible. Then this is also a form of testing known as exhaustive testing. That is, you test all possible inputs. Now, suppose that there's a procedure which takes two integer parameters, x and y. And if you assume a 64-bit computer, then with these two parameters, you have 128-bit string. So there are 2 to the power 128 possible inputs. Right? You can, even if you assume that you are efficiently keying in an integer pair in 10 seconds, it will take billionaires to enter all possible values. Right? Automated testing also has its own problems. The basic problem is, that is the second aspect, is how do you know what is the expected output? It is a chicken and egg problem. The question is, if you knew what is the output for all possible input, then you actually have a correct program which solves the problem. Then why do you need this program? If you know the correct output for all possible values of input, then you don't need this program. You need this program because you do not know that. And therefore, exhaustive testing or testing, almost exhaustive is impossible and ruled out. Right? So that we cannot look at that. We have to be smarter. The fact remains that it consumes a large effort among all phases, largest manpower. This slide says 50%. I mean, I think I picked it up from some earlier version of the slide I used. But the current statistics is about 70% of software development effort goes in testing. So it is getting more and more complex, sophisticated every year, because you have larger and more complex programs. You are embedding them anywhere and everywhere. You have embedded systems, you have handhelds, you have IoTs, you have fog computing, all of that everywhere. And every new paradigm you bring in, it comes with its own challenges of testing. Okay, so let us, just at the first level, let us try to look at the overview, take an overview of the testing activities. Certainly, the first thing is to do test plan and design the test suite. Then run the test cases and observe the results to detect failures, debug to look at the errors, and correct the errors. This is a normal life cycle you all are doing. So you can have errors, faults, failure. A failure is typically a manifestation of an error or a defect or a bug. We will often differentiate between a failure and a bug, right? Because a bug or an error may exist, but it may not lead to a failure, right? You know it is a bug only when it bugs you. You do not know otherwise, right? So only when it leads to failure, you get to know that. But that does not mean that it did not exist, right? So that's a big challenge of the testing, right? You have bugs, you do not know about them. When you get to know them, the system has failed. Then it's too late. So how do you solve that problem? The other aspect is so exhaustive testing is not possible. So what you are doing is kind of doing some kind of sampling testing or some random testing, or many of the techniques we'll look at. So the question is, if you repeatedly test, do you improve the system? The answer is no. It's called the pesticide effect. That is, if you apply the same test technique number of times, one after the other, then the second application of the technique or the third application of the technique does not detect new bugs. Quite obviously. This is called the pesticide effect, because if you apply a pesticide, then you kill a certain type of pests, but the types which are not killed will not be killed by the application of the same pesticide. You need to use a different one. So similarly, for finding more and more bugs, you need to have different fault detection techniques. So kind of if you just do a back of the envelope computation, then let's say we have 4 fault detection techniques and say 1,000 bugs. I mean, this is a hypothesis. And if we say that each detects only 70% of the bugs, then these detection techniques applied one after the other, how many bugs will remain? So at every stage, since the respective method detects 70% of the bugs, 30% of the bugs will remain. So it is 1,000 times 0.3, 0.3, 0.3, 0.3. If you do, then 81 bugs will still remain. And so you can see that the more and more you go, the more and more you test and make a system bug free, it gets more difficult, more expensive to find the next bug. But you after all that, you don't want to board a Boeing or Airbus flight which you suspect has even one bug, right? So that's a kind of problem. So things often will have to be looked at in a different way. You try to visualize different kinds of fault models. Fault models are models which say what faults are possible in a program. Now, of course, certain faults you can rule out because you know that they will never happen. You can possibly prove that also. For example, a concurrency-related problem in a sequential program will not happen. So just to illustrate that, I mean, what kind of bugs we have left out in whatever we have discussed. Consider this implementation of the singleton. I'm sure all of you are singleton experts now. This is using the earlier design that I had discussed. So I have a printer with parameters. There's a constructor which is private. And there is a static printer pointer, which is private, which is supposed to keep the pointer to the singleton. I have a destructor in the public so that later on it can be destructed. And then I have a printer function, which actually gets me that singleton printer. So what it does is it checks whether this pointer is null. This, my printer pointer is null or not. And as a static declaration, as a static definition, I have set it to null. So before any call to this can happen, this has become null, supposedly. And then I check that. If it is null, then this becomes true. So I create a new printer and return that value. And since this pointer has been set, for all subsequent checks, this will be non-null, right? So we are happy with having implemented a a singleton very successfully. Right? Now, let me just highlight two bugs in this. One is the bug that can happen in a concurrency environment. Suppose you have multi-threading, right? And there are two threads. Incidentally, both of them are trying to access this printer, which is quite logical. And for the whole system, this is the first access. Right? So what happens? One thread enters this function. One thread of control enters this function. At that point, printer pointer is null. So it checks, gets this condition as true. And before it can do the new and set it there, it has timed out. At this point, the second thread gets in. Second thread is also trying to access this function. Naturally, the first thread did not do the new and set the pointer. So pointer is still null. So the second thread also get this as true and will get in here. Subsequently, both the threads, when they get time, they construct the two printers. Whoever constructs it later and sets it to the printer object remains there and will be used subsequently. The one who has set it first will get licked. And if that printer has a lock in the printer construction, if the printer has a lock, then because it needs to do spooling, so the first object created has held that lock, and you are using the second object that got created, which does not have that lock. So you'll have complete mess. Now, this is a problem which is, you can see, is a concurrency problem. So we were happy with this solution because we felt that, well, this is a sequential environment. So this will work. That cannot be a problem in that. So it's true. I mean, in a sequential case, this is fine so far as concurrency is concerned. There is a second question, which is interesting, and which is a problem for a sequential program also. You have set this as static, this static as null, right? I'm just trying to give you insights into how does your fault model gets complicated, or the way you have to think. So this will be set as null, right? So this is a static initialization. Remember that in C++, in C, the static values are initialized before main starts. And they are done in an arbitrary order. Arbitrary in the sense that, like, you can say that the data members of an object will be initialized in the order in which they are listed in the class we discussed. Nothing like this exists in terms of the static. When they will be initialized, when they will get constructed is not known. You cannot. Now let us see. Now this function is a static function, right? So it is possible that I have some other class which has a constructor, and that constructor uses this printer function. It's quite possible. And I have a static object instantiation for that class. So I have one static object being instantiated, so its constructor will get called, and that constructor calls this printer function. And I have the initialization of this printer pointer. Both are statics, so their initialization order is not known. So if I happen to initialize this pointer first, and then that object gets constructed, everything is hunky-dory. My test pass, I'm very happy. But in a different system, what can happen is that object gets constructed first. When that object gets constructed, that constructor calls this function. Now think about the status at that point of time. This memory, my printer pointer memory, has been bound. It is a valid memory. It can be accessed, but it has not been initialized. This is not an object, so it does not need a constructor. So this can be accessed pretty well, but this has not been initialized to 0. So in all likelihood, the object constructor which is accessing this printer function will get some non-zero value here, assuming that the printer exists, which is a garbage. Tries to dereference that, the program crashes, and you have no clue why is it crashing here. Right? Logically, it looks right. Right? So that is what is kind of the insight you'll have to carry in terms of defining the fault model. In the first case, my fault model, I was discussing about concurrency. That if I have concurrency, then at every stage I have to analyze this concurrency. Now we can actually I can make a comment also on this this particular singleton design, that at least the bug that I mentioned in terms of initialization of static will not arise if you use a Myers singleton, because it's a local static object, right? So it is not dependent on some other object being initialized before it, right? So that's another advantage of a Myers singleton object. Whether it is fault tolerant to concurrency is something that I'll leave it to you, because you have not done concurrency much. But what I'm trying to show is your fault model needs to consider both of all of these kind of factors. So in one case, it is a concurrency model that needs to be considered in designing your test plan, in designing your test suite, test cases. And in the other, it is the fact that the ordering of initialization of static values is arbitrary and happens before main starts. So it is before you take control of the program, is a fact which has to be built into the fault model, is what you might have to expect to happen in the program. Right? So based on that, there are several work done in terms of classification of fault models. I just given examples from two domains. One is object-oriented programming, which is what we are more dealing with here. So object-oriented faults are grossly classified in terms of two kinds of models. One is algorithmic faults, which is primarily in the procedural part, that is the logic written correctly, so which will often lead to incorrect result or inadequate performance and things like that. Other could be structural faults, which is procedural faults in terms of not being able to invoke the right procedure. It could be traceability faults. It could be other object-oriented faults in terms of object creation, the lifetime, and so on and so forth. So your fault model will have to consider all of these different aspects. One other domain I can mention is, I'm sure you are doing computer, hardware lab and all that, and you may have come across this already, the hardware fault model. Some of the typical faults that happen in hardware. There are several, of course. One is stuck at 0. That a point which should have had a value is stuck at 0 or stuck at 1. Or something has got open circuit, something has got short circuit. So you make models to test for the presence of each one of them. Right? And kind of hardware testing more often goes, to a very good extent, on a fault-based testing. That you make more and more models. There are dynamic models also. It's not only, these are more like static models, but dynamic models also, for example, which happens at higher frequencies and so on. But you primarily drive it to the fault-based model. You have a similar approach in software testing, but often the fault model itself may be quite complex. Just a simple example of singleton showed you, kind of difficulties that we might get into. So we primarily, rely on designing test cases. And how we design them is a question of the models and strategies. So each test case typically tries to establish correct working of some functionality. in talking in very general terms. So it executes or covers some program elements and restricts the type of faults and fault-based testing. So to test a software, we need to carefully design test cases. And the collection of all test cases is a test suite. You saw a little bit of that in the fraction class unit test I included in assignment 3. We can blow that up further and make it a complete test suite. But that is kind of the approach. So a test case is a triplet. It has an input, the data to be input to the system. It has a state of the system at which the data will be input. In some cases, this state will be the startup state. That you have just started, you are giving an input from the std in. But it could be that you want to test a very particular function. You want to test a particular situation in the code. So under what condition you want to give this input is also very, very important. We'll talk about this more when we talk about directed tests. So we have so far looked at the test cases as just a doublet, the input and the expected output, which are quite understandable. But in actuality, a test case will be a triplet of the input, the state of the system when you give that input, and the expected output. It may be that you give the input from your input stream, but not at the beginning, after certain things have happened. It may be that you inject the input somewhere in the middle of the code through your debugger by setting the value of a variable. So that is at a certain point, there is a certain state. So these triplets have to be carefully designed. And the set of all test cases that we design by this is called the test suite. Right? So we'll talk a lot about that. The expected output is often called the golden. Okay. Now, so that's about the fundamental definitions. Now let's see what we are really trying to do. So we will talk about two terms commonly. One is called verification, another is called validation. You have heard about this when we are discussing the V model in SDLC also. So verification is a process of determining whether the output of some phase of development conforms to the previous phase. So you have different phases. Now, you do not know at a particular phase, you do not know whether your previous phase was correctly done. But assuming that your previous phase is correctly done, you want to ensure that the current phase is correctly done as well. So we are checking if we are building the system correctly. So verification is concerned with phase containment of errors. That as much errors are possible to be contained in the design phase, we should try to do that. As much errors are possible to be contained during the development phase, we should try to do that. Given that, assuming that the previous phase was okay. Right? If we can do that at every stage actually correctly, then you have it. Validation is more checking out if the correct system has been built. Right? We talked about these two aspects. So it is whether the fully developed system conforms to its SRS. If it does, then it is validated. It is correctly built. That is, the aim of validation is to ensure that the final product is error-free. Right? So these are the two things that we will always keep in mind. So in terms of the design of test cases, let's try to get a little bit more into the approaches. So exhaustive testing of any non-trivial system is impractical. We have already discussed that. So we need to design an optimal test suite of reasonable size and uncovers as many errors as possible. Right. So exhaustive testing is at one end where you have everything in the test suite. It is of unreasonable size, unreasonable testability, and it will cover everything, of course. Now, if you do not, other extreme is you do not test anything, then you have a very reasonable size, you have no work to do, but you will not uncover any error either. So you have to drive a balance between them. And how do you use a smaller test case but cover more errors is where the smartness really goes in. So if the test cases are selected randomly, that's one way of testing, monkey testing. That is, if you put a monkey in front of the keyboard and let the monkey type in, then many tests would not contribute to the significance of the test weight. It will probably test the same thing over and over again and would not detect many errors that could have been detected by other tests in this weight. So the number of test cases in a randomly selected test weight is not an indication of effectiveness of testing. We still do random testing, still is a method, and is still recommended, because after you have thought through everything, after you have done everything, if you just generate a random test case, then there's a good likelihood that it gives you a situation which you may not have thought of. Right? So random tests are more not for guaranteeing that you do not have bugs, but they are more like indicative of if you're left with something that needs to be brought into the analysis. But in general, no. So because I may use a large number of random selected tests, but that I cannot conclude that the many errors have been covered really. Now, let's say a very simple example of what I mean by optimality. It's very trivial example. So I'm trying to, this code is trying to find the max of two integers, x and y. You'll get the bug in a fraction of a second. If x is greater than y, max is x. Here it should have been, max should have been y, which is not. Okay. The question is, what will bring out this error? So if I have x is 3, y is 2, I'll correctly get the result 3. If I have x is 2, y is 3, I'll get the result as 2, I'll get the bug. Now suppose I have a larger test weight, 3, 2, 4, 3, 5, 1. I have more number of tests, a bigger weight, but I'll not get the bug. Because in every case, actually I'm testing, I'm giving inputs where x is greater than y, whereas that bug exists when x is less than y, right? Or at least when they're equal. So that is the whole, this is a pathologically simple example, but that is the whole idea, that you have to ensure optimality so that you test the possible things that can happen, have representatives for those, check for boundary conditions. And once you do that, then you expect that you have covered a large number of possible bugs. So this has been formalized into variety of, design of optimal test weight has been formalized into different approaches called black box approach, white box or glass box approach, and gray box approach. So the black box testing is a method where you take your entire system as a black box. So as if your end user is testing. End user does not know all C++, all classes, all threads, all network packets and all that. The end user knows that if I give this input, this should happen. Right? So it examines the functionality of an application without peering into its internal structure or workings. Right? So that's the black box testing. And it can be applied to virtually every level of software testing: unit, integration, system acceptance. I will define unit, you already know. Integration, somewhat you know. System acceptance, I'll slowly define more. So here in black box testing, the test cases are designed only on the functional specification of the software, because you are assuming that you do not have the internal knowledge. And that's important. That's important. How do you see the system as an end user? So the black box testing, therefore, often is also called functional testing, or it's called specification based testing. So more often you will design the black box test cases based on the specification or at more the analysis of it, but not the design, because you're not looking in. White box testing or class box testing is a method of looking inside. A method of software testing that tests internal structure or working of an application as opposed to its functionality. So white box testing is not only looking at functionality, actually primarily it is not looking at functionality, but it is looking at the internal of every module, if every module is working fine, if every class is working fine, if interfaces are working fine, so on and so forth. It is testing an internal perspective of the system. As well, it can prove to be a test for the programming skill that I used to design the test cases. So designing the white box test cases requires knowledge about internal structure of software. So it has to happen after, it can happen after the design phase starts. And it could have high level testing cases, it could have LLD test cases, and so on and so forth. Naturally, since you are looking at the internal structure, white box testing is often called the structural testing. Finally, gray box testing is a combination of white box and black box testing. For example, say it could be that you do a gray box testing at a module level. You take every module as a black box. Maybe there are 3 or 4 modules. You take every black box as a module, taking their specification as designed, and test them as end user. So you are doing a black box testing. But the fact that you know what the modules are and how they interconnect and how the messages pass between them, you are doing a white box testing. But a general black box testing is completely opaque. A general white box testing is completely transparent. The gray box testing is somewhere in between. The level of abstraction you use for gray box testing depends on what kind of test design you are doing. So let us get a little bit into black box testing. Now, there are various approaches, but 2 of them are notable, which is common sense but structured. One is called equivalence class partitioning. That is, as we argued, that it is not possible to do an exhaustive testing. The number of possibilities could be very, very high. The same thing applies for finding the max of 2 numbers. But logically, you can think that, well, if I have to find the max of 2 numbers, then these numbers could be in 3 equivalence classes. Numbers pairs where the first number is larger. The number pairs where the second number is larger. And the third equivalence class is pairs where both numbers are same. Right? So you can say that if I partition my total potentially infinite or extremely large input space into 3 equivalence classes and use some representative for each class, then I should be able to become confident that I have tested moderately well. The other approach is called the boundary value analysis. That often the programs work at the general value, but does it work at the boundary value? For example, one kind of boundary value analysis, I'm taking example from white boxing, but the concept is the same. We write a loop. There are 2 boundary values we always have to check. Does it start rightly? At the initial index, does it start rightly? And does it end with the right condition? I'm doing n iterations. Does it go from 0 to n minus 1, or it goes to 1 to n, or whatever? So I need to check for a general I. That's a general testing. But these boundary conditions, the general stuff might work fine, but the boundary condition may not. So that's called the boundary value analysis. Right? So these are the 2 main approaches of testing. I mean, black box test design, not testing, I should say. So as I said, you take the input data. Suppose you are if you are specified by a range of values, then you can say that the numbers between 1 to 5,000 is what is my specification. So I can say I have 3 equivalence classes. One is less than 1, invalid. One is more than 5,000, invalid. And one is between 1 and 5,000, which is valid. So 3 equivalence classes. We can have an enumerated set of values. We can have a test suite based on this range of values, saying that, well, what do I test? For a number being within 1 and 5,000, I'll test one which is less than 1. I'll test for -5. I'll test for one which is in the middle within this range, say 500. And I'll test one which is more than 5,000, which is 6,000. So I say that -5, 500, 6,000 is a reasonable. I'm saying reasonable. Nothing is sufficient. It's a reasonable test suite for the taking inputs in the range between 1 to 5,000. So let's just, I'm showing some more examples of equivalence class partitioning of the input. So max I already talked of. So you can say that I have 3 equivalence classes for max: x greater than y, x less than y, x equal to y. So I'll if I logically reason that, then I can have test cases. So at least these 3 test cases are required to get a minimum confidence on this black box testing. That is my test suite. And as you will find that in most cases, this will be enough to test the larger of 2 numbers. Take a little bit of a different program, QES program, quadratic equation solver program. So it takes a quadratic equation ax squared plus bx plus c equal to 0. So it takes 3 coefficients a, b, c and tries to find the solutions of x. Now, if you look into the partition space of possible solutions of this equation, you'll find that there are several possibilities. One is you can have infinite roots if all of them are 0. Right? Any x is a solution. If a, b, c all are 0, then this is vacuously 0. So infinite possible roots. If you have a and b as 0 and c is not equal to 0, say 5 is equal to 0, then you know that you cannot find a value of x which is a solution. So you can do no root. That is another equivalence class. So I'm just trying to separate out the equivalence classes of A, B, C, this triplet. So which is if A, B, C, each one of them, even if I consider them to be integer, then it is integer cross integer cross integer. Sum. Then there's a case of A being 0. So in each case, you will have only one solution for x, b not equal to 0. So there's a single root. If I have a not 0 and this, what you say is a discriminant, b square minus 4ac is 0, then you know that we have 2 roots and those roots are equal. So that's a repeated root case. I will have distinct roots if a is not 0 and the discriminant is positive. I'll have a pair of complex roots if a is not equal to 0 and the discriminant is negative. Right? So I don't know if you can analyze and get other equivalence classes here, and considering how many of a and b and c can be 0 and the value of the discriminant. I think this exhausts all possibilities of equivalence. So that huge space of integer cube is resolved into just 6 equivalence classes. And I can have a representative test case for each one of them. So if I test with this 6, my QES program, then I have a fair expectation that it will go right. Mind you, I'm doing black box testing. So I do not know how the computation is done. So I'm not looking into considerations like what if there is a floating point overflow underflow error when you do this multiplication in b square minus 4ac. I'm not doing analysis of whether I can have floating point error finding the square root or doing the division by 2a and so on. Those all are beyond this because I'm just doing black box testing. So I'm looking at, in terms of the input space, what are the equivalence classes that are possible. Similarly, I can do a boundary value analysis. I talked about this. So what happens at the boundary of the test cases? So let's say in the checking for 1 to 5,000, earlier we just looked at 3 equivalence classes: below 1, above 5,000, and in the middle, minus 5, 500, and 6,000. I'll say I'll take the boundary value also. So 0 is from the first equivalence case, less than 1. 5,001 is more than 5,000. Then I take the 2 boundary cases also, 1 and 5,000. I can take the third equivalence case in the middle, but what is important is to check that at these 2 boundary cases, it works. So that is called the boundary value analysis. Similarly, for the QES program, A is 0 is a boundary. So you have to check whether it works perfectly there. This is a boundary. And as we'll see that in terms of the white box testing, this will become a serious condition because it can actually be 0, but when you compute in floating point, this might not turn out to be 0. Right? So white box testing will have quite a significance for this. And if I have this boundary condition checked, boundary value analysis checked, then I will have a good possibility of finding out if I had error. So this repeated root case is a boundary value here. These 1 to 3 are boundary values here, which I will obviously. So in terms of QES, the boundary values are getting covered by the equivalence partitioning itself. It may happen, it may not happen, but that is how. So I think that is what we have time for today. So we discussed about the overall requirement and approach to testing, coming down specifically to test case design using black box and white box approaches, and talked about the equivalence class partitioning of the inputs and boundary value analysis for the black box testing. If there's a quick question, I can take that. Anything that
Sir, can you give an idea of equivalence classes in case of the railway booking system, considering all these stations?
Why should I?
Like this was a problem which even I was facing when designing the test cases. The thing is, in a different way, putting the things into equivalence classes is like easy when we are in some sort of like a logical or mathematical domain. Like we have fixed scenarios, but when we are designing applications for real world scenarios, like everything is different. So like how do
No,
we
not
define these
everything is
equivalence
different.
classes?
Say, I will first say that for station name, there are 2 equivalence classes. One is a valid string, one is an invalid string. Empty string is not valid. So you call it boundary value, you call it equivalence class, is a different equivalence class from a station name Mumbai or Delhi or Kharagpur, right? So that's one kind of. You can consider whether you want to have non-alpha in your station name. If you do have, then you have 2 different equivalence classes there, right? In terms of distances, you have multiple equivalence classes. One is negative or 0 distance is not possible. It has to be positive distance. One is pair of stations have to be different. One is symmetric stations belong to the same equivalence class. One is yeah. So these are the broad equivalence classes. So you don't need to check for every pair of Mumbai Delhi, Mumbai Bangalore, Mumbai Kolkata, Kolkata Bangalore, Kolkata Delhi. No, not each one of them. Right? Does it give you a sense? I mean, you have to take it in that sense. I mean, it's not that. And you can define equivalence classes for checking on the categories, on the booking class, on the booking itself. Maybe it will it will. This is a little bit more complex problem, so it will grow a little bigger. But does it making sense what I'm saying?
Yes, sir, it made sense. But still, like the problem that the data was loaded correctly is not testable unless we exhaustively test all scenarios, right? Like there may be an error in like a certain pair of stations have incorrect distance loaded into the system. Like these small errors cannot be detected unless it is exhaustively tested.
See, you are getting to a very different domain of testing, which is testing your data. We are not talking about that here, right? You're talking about the distance is 1443. You have inputted as 443, right?
Yes.
That's a data validation, right? Which has a very different kind of approach, and mostly automation works pretty well there. And that is the reason that you'll find that very rarely you will have data coming in from the raw input. It will possibly come from a database which is already validated, and then you are having updated data onto that. That again will have to get validated and so on. Do not confuse between initialization data testing vis-a-vis the software testing. Your code has no problem in this. You have given it a wrong data. What can be done? Right? Are you getting my point?
So two separate domains of
These
test.
are two separate domains. So you are getting a correct fare for a wrong distance. That's not your fault. That's not your domain. You have to check that you don't accept a negative distance. You have to check that you don't accept a booking where both stations are same. You have to check that you don't reject a booking where the distance was given between Delhi and Kolkata and the booking is from Kolkata to Delhi. Given that the distances are same on both ways, it is actually not, but if we assume that, right? So this is in your domain. But whether those values are correct, whether the percentage of concession is correct, whether the cutoff date for senior citizenship is correct, that's for the data validator's job. That's a different issue. Right? That is not something that I mean that we will have to be concerned with, but that's more of a different domain. And at least in this series, we are not talking about it. Actually, when we talk about databases, we talk more about these cases. Yep.
So why do we concern ourselves with checking for negative distance? Because if we have negative distance, we'll get negative fare, and that's again a wrong in data input. As long as it doesn't crash the system.
That's a known constraint that distance cannot be negative.
It's a simple enough thing to check.
Yes, it's simple enough to check. I'm not saying it is complex, but I'm saying that is an equivalence class. So if you have not checked, sure, then you will have a test case which will give a failure.
Yeah, definitely.
It will go through which it will not throw the exception that it should throw. Right, so it's a failure.
Yeah.
It is, see there are failures of two kinds. One is a positive case does not go through, and the other is a negative case does go through.
Yes.
Right. So we'll talk about that, positive tests and negative tests and all that. Right. So you will do reasonably everything, given that you have a correct data according to the conditions given to you. You will produce a correct result
within the constraints of garbage in, garbage out.
Yes, because certainly you have no knowledge about what the distance is, so you cannot be expected to correct that, neither check for it. You have no control on the regulation of senior citizenship, so you have no way to check that.
But
so that part will have to be
a non-negative, so we can check for that.
Yeah, yes.
Good. I get the idea.
Right. For example, you get a passenger with a date of birth, which is after the date of booking. Right, I'm 23rd March, and you get a passenger whose date of birth is 30th March 2021. You must error out in that. You cannot say that I do not know, because that gives a negative age, which should not be acceptable. Right. But you are doing a booking today for a date which is 21st March. You should error out in that, because these are logical inconsistencies. But somebody wanted to do it for 27th March and inputted 31st March. That is not something that you can detect or you are expected to do.
Right.
Right.
So within the given domain knowledge we have, we test for that.
Right, right. And that is the reason you often go back to the customer and ask also.
Yeah. What's what?
What is what? For example, what is the definition of 60 years? I mean, this happened, I mean, very recently to me in the COVID vaccination. My date of birth is in July 61. So according to, if you compute age, I'm 59 plus. The question is, am I eligible for the senior citizenship? Now, when I tried the registration, I found that they have taken a very simple logic. They have just taken the year of the birth, not the date. So by year of birth, I'm 60 years. That depends on what interpretation that specification has given you. But if I take it the actual, then I'm 59 plus. I'm not eligible for the vaccine. Right. So that's the kind of shades. Oh, we have crossed the time like anything. It was nice discussing, but please keep, if there are more questions for tomorrow, we will discuss it tomorrow. Bye. Have a nice day.
Thank you, sir.